Jai Hind everybody. My name is Nandita Goyal and I am working as an assistant professor in AKGEC Engineering College. Today I will be covering the topic recurrence relation, which is a part of DSTL subject. The contents that I will be covering in this lecture include what is actually a recurrence relation. Then we will be discussing what do we mean by a solution to a recurrence relation. Then we will be discussing different types of recurrence relations which are there, like first order linear recurrence relation. Then we will be discussing a solution to this particular type of recurrence relation. Next we will be discussing a second order linear homogeneous recurrence relation, and we will also be discussing the solution to this type of recurrence relation. When in the solution part, we will be discussing how to solve a recurrence relation of this type if the roots which we find out are real and distinct roots. And we will even discuss a question based upon how to solve a recurrence relation if the roots which we find out are of repeated nature. At last, we will be discussing what are non-homogeneous recurrence relation and how do we solve such type of relations. So, to start, first of all, we will look at what exactly is a recurrence relation. This term recurrence relation actually comes from the word recursive function. When we study recursive function, we actually see that how it works. So, when we talk about a recursive function, it means that a recursive function is basically a function which keeps on calling itself. It will call itself until and unless a base condition is met. Once the base condition is met, it will terminate from there. So, this term recurrence relation comes from that particular term, that is recursive. So, if I talk about a recurrence relation, it is nothing but actually it is a sequence which can be defined by giving a formula for its nth terms by writing its previous terms. That is, we describe a formula in terms of the previous terms for the nth term of the formula, and such a relation is known as recurrence relation. The alternative approach is to write the sequence by finding the relationship among the different terms of the relation, and such a relation is known as recurrence relation. We even call such a relation as difference equation. So, difference equation is also nothing but recurrence relation. So, here there is an example. Suppose I have a sequence S which contains these terms, that is 5, 8, 11, 14 and 17 and so on. Now, here the initial condition is defined as S1 is equal to 5. This S1 is nothing but this is actually the first term for this sequence. So, the initial condition for such a relation is given as its first term. Now, how to define a relation for this type of sequence, and I want to define a recurrence relation. So, I have given this formula Sn is equal to Sn minus 1 plus 3. So, now what is here Sn? Here Sn is nothing but the nth term of such a sequence, and what is this Sn minus 1? This is n minus 1th term for this sequence. So, what is the meaning of that? The meaning of this is that I am defining the nth term for this sequence in terms of n minus 1, that is the previous term plus 3. So, this is nothing but a recurrence relation because I am able to define the nth term in terms of the previous terms, and this was the basic definition of a recurrence relation. That is, if we can define it by giving a general formula for the nth term or by writing few of its terms, if I can write the formula in terms of the previous terms. Now, let us see how to find out the different terms, that is these terms. So, I already know that my S1 is equal to 5. Now, according to this formula, if I want to find out S2, this will be equal to Sn minus 1, that is S1 plus 3. Now, I know that the value of my S1 is 5. So, 5 plus 3 is nothing but 8. That means 8 is going to be the next term, which is this one. Then suppose I want to find out S3. S3 will be S3 is equal to S2, that is Sn minus 1 plus 3. So, this will be equal to S2 is 8, 8 plus 3 is 11. So, my third term is going to be 11, this is it. Then coming to S4, S4 is previous term plus 3. So, this will again be equal to 11 plus 3, that is nothing but 14. So, my next term will be 14. And last one, that is S5, S5 will be equal to S4 plus 3, which is 14 plus 3, that is equal to 17. So, the next term is 17. It means that I am able to find out all the terms with the help of the previous term. So, this is a recurrence relation for which the initial condition is given to me and I can find out my terms. So, this is the basic definition of a recurrence relation. Now, here I have one more example for the same, that is find the first 4 terms of each of the following recurrence relations. So, the recurrence relation which is given to me is AK is equal to 2AK minus 1 plus K for all integers where K is greater than equal to 2 and the first term A1 is given to me as 1. So, how to find it, or just see whether it is a recurrence relation or not. Just see the term AK, that is the kth term, this is nothing but the kth term. I am able to find out this kth term with the help of the previous term 2 times into the previous term plus K. So, I already know that the initial value is given to me as 1, A1 is equal to 1. So, if I want to find out A2, now A2 will be equivalent to 2 into previous term, that is A1 plus K is nothing but, now I am trying to find out the second term, that is plus 2. So, this will be equivalent to 2 into A1, that is 1 plus 2. So, this is nothing but 4. So, first I have find out the first term. Now, I want to find out the third term. Third term is 2 times into A2 plus K. K means 3. So, this will be equivalent to 2 into 4 plus 3. Okay. So, the next term will be 4 into 2, 8 plus 3, that is nothing but 11. So, I have found out the third term. Now, what about the fourth one, that is A4. A4 is 2 into the previous one, that is A3 plus K. K is 4 because I am trying to find out the fourth term. So, this will be equivalent to 2 into 11 plus 4, that is nothing but 26. So, now I have found out the first 4 terms, that is the first term is 1, it is already given to me, then the value of the second term is 4, then 11, then 26. So, this is the solution to this question. This is 1, 4, 11 and 26 and so on. So, this is how we solve a recurrence relation in general. Now, if I want to give a particular solution to a recurrence relation, what is actually it is? The solution to a recurrence relation is that we are able to provide an explicit formula which will satisfy the recurrence relation with the initial condition which is already given to me, and this is actually known as solution to a recurrence relation. Now, whenever we talk about a solution to a recurrence relation, we will first have to see that what type of recurrence relation is it to which we are trying to provide the solution. So, starting with the very first type 1, that is if I have a first order linear recurrence relation. Now, let us focus on these terms, first order, then linear and then recurrence relation. So, when I say first order, it basically means that my nth term or my n plus 1th term will be only dependent upon one previous term. Like if I see this example, a n plus 1 is equal to 2 into a n. That means my n plus 1th term is dependent on only a single term, that is a n, one previous term, and I am given this initial value. So, how to solve such a recurrence relation? Now, this is first order because my n plus 1th term is dependent only on one term. That is why it is a first order linear recurrence relation. Now, the general procedure to solve this type of recurrence relation is, first of all, I will form a linear equation from this given equation. Then we will convert this particular equation to R format. After converting it to R format, I have to find my root R, and then the general solution to this first order linear recurrence relation is given as AN is equal to capital A, where this capital A is nothing but a constant, into R to the power n. Once we have found the value of this root R, we already have some initial value for A, then we will find the value of this constant A. This is the last step. So, we will just see with an example how to do it. So, first of all, we will try to solve this particular example which is given to me. Now, here I have this equation AN plus 1 is equal to 2 to the power AN, and the value of A naught is given to me as 1. So, first of all, I will convert it to R format. So, to convert this equation to R format, I will just write it as R to the power n plus 1 is equal to 2 into, then in place of an, R to the power n. So, this is my first step in which I have converted my equation to R format. Once I have done this, I need to find out the value of this R. So, to do that, the next step is divide the above equation with lowest R value. So, if I see what is the lowest R value in this equation, here the value of R is R to the power n plus 1, and here it is R to the power n. So, R to the power n is less. So, we will divide the entire equation by R to the power n. So, what I will get? R to the power n, when we will divide here, I will get an R, and here this will be cancelled. So, I will get 2. So, that means the value of my root R is 2. So, the first thing I have done, that I have found the value of this root R. Now, I know that since it is a first order linear recurrence relation, the general solution to this can be given by the equation AN is equal to capital A, which is a constant, into R. R I have already found to be 2 to the power n. Now, I already know that A naught is equal to 1. So, that means here the value of n is nothing but 0. So, I will substitute this value in this equation 1. So, in place of n, I will substitute 0. So, I will get A 0 is equal to capital A, I do not know the value, 2 to the power 0. Now, the value of A 0 is nothing but 1. So, 1 is equal to A into anything to the power 0 is 1. So, I directly get that my A is equal to 1. So, now I will substitute the value of A is equal to 1 in equation 1. So, what I will get? I will get AN is equal to 1, the value of this A, into 2 to the power n. So, this is the solution to this question. This is how we will be solving this question. Now, we have another example. Let us first see that what type of relation this is. Since my nth term is again dependent only on one term, that is a n minus 1, this is again a linear first order recurrence relation. Now, to solve this, first step, as we have done earlier, that we will first convert this to R format. So, we get R to the power n is equal to 7 R to the power n minus 1. Now, once I get this, let us see that what is the lowest power of R through which we will divide the entire equation. So, the lowest power here is R to the power n minus 1. So, we will divide the entire equation with this value R to the power n minus 1. Dividing the above equation with. So, what we will get? we'll get a r over here. R is equal to 7. So we have found out the value of root. So this is my root value. Now since I know that this is a first order linear recurrence relation, what is the general solution to this? The general solution to this is an is equal to capital A, which is a constant, r to the power n. Now I already have the value of r, that is 7. So an is equal to capital A into 7 to the power n. Now let's see what is the initial condition which is given to me. It is given to me as A2 is equal to 98. That means the value of n here is nothing but this 2. Let's substitute this. So now I get, in place of n I substitute 2, A 7 to the power 2. Now A2 is already 98, which is given to me. So 98 is equal to A dot 49. Now what will be the value of this constant A? The value of this A will be nothing but 2. So now I even get the value of this 2. So I'll just substitute this in my standard solution. So I'll get an is equal to 2 into the value of r is 7. 7 to the power n. So this is my solution to this question. So this is how we solve linear first order recurrence relation, where our nth term is dependent on only one previous term. Now moving ahead, we will just look what do we actually mean by a second order linear homogeneous recurrence relation. So when I am talking about second order, that means it will be something like this. Why? Because now just see that if I look here, my n plus 2 term will always be dependent upon n plus 1 as well as nth term. So here the n plus 2th term can be expressed in terms of n plus 1 as well as nth term. So we call it as a second order linear recurrence relation, and since it is equated to this 0, it is a homogeneous recurrence relation. Now how to solve such a recurrence relation? Almost the basic procedure will remain the same, that is whatever equation is given to me which is of second order, I will just convert that to R format. Once I have converted it to R format as we were doing previously, we will divide the entire equation with the lowest value of R, whatever is the lowest value of R over there, then we will find the roots. Now whenever we will find these roots, I can have real roots, and both, since we will get a quadratic equation, whenever we will solve that quadratic equation, the roots which I get, these both the roots can be real and distinct, their values can vary from each other. Or in second case, what I can get that both the roots are real and both the roots are even equal. So in both these cases, my standard solution will change. So in first case, the standard solution will be an is equal to capital A, which is nothing but a constant, r1 to the power n plus b, which is again a constant. This is my second root, r2 to the power n. And when I will have equal roots, that means r1 will be equal to r2. In this case, the standard solution will be a, which is again a constant, into r1 to the power n plus b, which is again a constant, and this n into r1 to the power n. Here r1 and here also r1, because both the roots are equal. So this is the standard solution. Now we will just see one example that how we do this. Now I have this example, an is equal to 5 a n minus 1 minus 6 a n minus 2, and I am given the two initial values of a0 and a1. So first of all, I will convert this entire equation to R format. So what I will get? I will get r to the power n minus 5 r to the power n minus 1, then plus 6 r to the power n minus 2 equal to 0. Now I will divide this entire equation with the smallest value of r. So the smallest value of r here is r to the power n minus 1. So what I will get? I will get a r square over here minus 5r plus 6 equal to 0. Now this is nothing but just a quadratic equation. So whenever I'll solve this quadratic equation, I'll get it like r minus 3, r minus 2 equal to 0. That means my r1 is equal to 3 and my r2 is equal to 2. So I have found out the roots. These are my roots of these quadratic equation. Now if I look at these roots, what type of roots are these? These are real and these have distinct value. So what is the standard solution which is applied in this case? The standard solution is a to the power n is equal to capital A dot r1 to the power n plus b dot r2 to the power n. Now I have to find out the value of this a and b. So to find out the value of this a and b, I'll substitute the value of n as 0 and then n as 1. So a0 is equal to capital A dot r1. What is the value of r1? The value of r1 is 3 to the power n plus b into what is the value of r2? 2 to the power, again this will be 0 and here also it will be 0. Okay, so that means this is my first equation, and then to get a second equation I will substitute n as 1. So I will get the value of this a, n I substitute as 1, a1 is equal to capital A into r1. The value of r1 is 3 to the power 1 plus b dot r2 is 2 to the power 1. So this is my second equation. Now I have two equations because I know that a1 is already 1 and a0 is also 1. So I just substitute the value. So I have two equations, I have two unknowns. So I can solve the value for this a and b. So after solving these two equations, that is equation 1 and equation 2, I get the value of a as minus 1 and the value of b as 2. Now once I have got these two values, I just have to substitute these values of a and b in my standard solution, which is this one. So I'll substitute this in this equation. So I'll get a n is equal to minus 1 r1 to the power n, where r1 is nothing but 3. So I can directly write it as 3 plus the value of b is 2 into r2's value is again 2 to the power n. So this is my standard solution. So this is how we can solve a second order recurrence relation if I have both the roots as distinct and real. Now we will see the second case in which both the roots will be equal and real. How to solve that? This was the solution to the previous question. How we have solved it. Now coming to this next example, although it is again a second order linear homogeneous recurrence relation, but here we will just see that the roots which we will get after solving the quadratic equation, both the roots will be real and equal roots. So for that, how to do it? First of all, we will convert this equation to again r format. So it becomes r to the power n minus 6 r to the power n minus 1. Then I have plus 9 r to the power n minus 2 equal to 0. Then I have these two initial values given to me. Now once I have converted the equation to r format, I will divide this entire equation with the lowest value of r, that is r to the power n minus 2. So I will get r square minus 6r plus 9 equal to 0. Now when we will solve this quadratic equation, I will get r minus 3 equal to 0. That means my both the roots r1 and r2 are equal and their value is equal to 3. So now looking at the value of these roots, I'll decide that that means the solution to this particular question will be of the standard form an equal to constant, then root to the power n plus b into n dot r1 to the power n. Okay, so now what all I have in this equation, I can substitute the value of n as 0. Okay, then r1 and r1 is what I already have. So I'll just try to substitute for n equal to 0. What will happen? It will become a0, that means 1. 1 is equal to a dot r1 is 3 to the power n. The value of n is nothing but 0. Then plus b dot, this will become, entire thing will become 0. So from here what I can see, that value of a comes out to be 1. Now I can form another equation for n is equal to 1. So when I'll form that equation, what I'll get? Now I have another equation, that is a1 is equal to capital A to the power r1. What is the value of r? The value of r is 3 to the power n. N is 1 plus b into n, that is 1 into 3 to the power 1. Already I know that the value of a1 is 1, the value of a is 1. So now from here I can solve the value of b. I have a single variable and a single equation through which I can solve it. So when I'll solve this, the value of b comes out to be minus 2 by 3. Now the value of a is 1, value of b is minus 2 by 3, r1 and r2 I already have. So I'll just substitute them in the standard solution and I'll get this as answer. The standard solution an is equal to the value of a dot r1 to the power n plus b. This was the value of b into n dot 3 to the power n. So this is the standard solution for this question. Now up till here we had talked about first order and second order homogeneous recurrence relation. Now let's see what a non-homogeneous recurrence relation is. Just see, when we are equating this, the left hand side equation is equated to 3 to the power n. Now this 3 to the power n is not a 0, this is actually a function of the type fn. So whenever we have this type of recurrence relation, we call it as a non-homogeneous recurrence relation. Now here the fn part is this one, which is given to me as 3n and the value of n is greater than equal to 1. So whenever we have to solve a non-homogeneous recurrence relation, so the general solution to such type of question is this one. This general solution is an is equal to anh, where this anh is the solution to the, because whenever we will have a non-homogeneous recurrence relation, it will have two parts. One part, if I equate this left hand side to 0, this becomes the same as a simple homogeneous recurrence relation. So we will have a solution for the homogeneous type plus particular solution for this particular type of non-homogeneous recurrence relation. So to find out the entire solution to such a question, we will have two parts. The first part, that is the solution to a homogeneous recurrence relation, and then the particular solution to this non-homogeneous recurrence relation. Now I have this table. So depending upon the type of fn which we are using in the question, we will have the solutions to this particular non-homogeneous recurrence relation. So if my fn is a constant value, anything like c, then it will be substituted in the particular solution with any value capital A, which is nothing but a constant. If my fn is of the type n, then in my particular solution it will be substituted by something like a1 n plus a0, where a1 and a0 are constants. Then if I have my Fn of the form n square, in that case my particular solution will be given in the form of a2 n square, where a2 is a constant, plus a1 n, where a1 is again a constant, and then a0. A0 is also a constant over here. And if I have my Fn in the form of something like r to the power n, so here my solution will be a dot r to the power n, where a is nothing but a constant. So if I look at this particular question where my Fn is of the form 3 to the power n, this is nothing but the form r to the power n. That means whenever I will talk about this particular solution, it will be of the form a dot r to the power n. So from here I will identify that which type of particular solution I am going to provide depending upon the Fn type. Now this is an example where the equation is, or the recurrence relation is actually a non-homogeneous recurrence relation. So I have my Fn as 3n, which is nothing but of the form r to the power n, and the solution to this is going to be a dot r to the power n. This is my particular solution. Now to solve this question, what I am going to do, I will first solve it as a homogeneous equation. So to solve this as a homogeneous equation, I have done nothing but, see, this is my homogeneous solution. So what we have done, left hand side is equated with 0 to make it homogeneous. So I simply get the equation a n plus 2 plus 3 a n plus 1 plus 2 a n is equal to 0. Now I can solve it like we were solving the questions previously. So I have just converted this thing to R format. So R format means r to the power n plus 2 plus 3 r to the power n plus 1, then 2 into r to the power n is equal to 0. Now we will divide it with the lowest value of r. So lowest value of r in this particular question is r to the power n. So we have divided the entire equation with r to the power n. So we get r square plus 3r plus 2 equal to 0. So this is nothing but a simple quadratic equation. So solving this quadratic equation, we get the roots as r1 equal to minus 2 and r2 is equal to minus 1. That means what type of roots are these? These are real and distinct roots. So the standard solution is a dot r1 to the power n plus b dot r2 to the power n. So this is the standard solution for this homogeneous relation. Now we have found out the first part, that is the homogeneous type of solution. Now to solve the particular type of solution, see, we have reached this point, that is particular solution. So a and p means particular solution. So now we will be equating this to 3 to the power n, because we are now trying to give a particular solution to a non-homogeneous recurrence relation. So now here the Fn is of the form 3n. So if I guess its form, it is nothing but r to the power n as I had written there. So the general solution to this is a dot rn, and here the value of r is 3. So the general solution is going to be a dot 3n. So now we will just substitute this a dot 3n to each position in the non-homogeneous equation. So we have substituted this. Once we had substituted this, from this particular solution, I will be able to find out the value of my constant a. The value of constant a after solving this equation comes out to be 1 upon 20. Now my particular solution was a dot rn. So this is my particular solution which I have got for this question. Okay, and my previous solution which was there for the homogeneous relation was this. Now to find out the entire solution, what we have, an is equal to an h plus an p. So h part I got from here and p part I got from here. So I just write it as an plus a, then I have the value of my roots, then this is my b, and this was the solution which I found here. So now again in this question I have my initial conditions given to me as a naught is equal to 0 and then a1 is equal to 1. That means we have substituted the value of n as 0 and then as 1. So, I have got two equations. Using these two equations and solving this, we get the value of A and B, that is both the constants. So, the value of A is minus 4 by 5, the value of B is 3 by 4. I have substituted both these values in the standard solution. So, this comes out to be my standard solution for this particular non-homogeneous recurrence relation. So, just we need to remember that whenever we are solving a non-linear non-homogeneous recurrence relation, I'll have to find out two types of solution. One is going to be the homogeneous part of the solution, and then the second one is going to be the particular part of the solution, and then only I can give the entire solution for a question. So, we have already discussed the recurrence relation solutions for three types. So, that was all for today. Thank you.